Okay, now we're going to start a subject on transformers. And in this lesson we have some objectives. First objective, the student shall be able to define a transformer. The student shall be able to distinguish the different types of transformers. There's a couple of different types we're going to discuss. The student shall be able to list specific terms as they are associated with transformers, so the different components that make up a transformer. The student shall be able to discern the difference between types of transformer losses. There are several different types of losses, and I want you to be able to tell me the difference between those. The student shall be able to calculate various transformer quantities with given information. So let's look here at the definition of a transformer. A transformer is a static electrical device. Static just means there's no moving parts. That transfers electrical energy between two or more windings through electromagnetic induction. And I kind of dive into this definition a little bit more with a couple more statements. A varying current in one coil of a transformer produces an expanding and contracting magnetic field. We learn this in the electromagnetism subject. When the voltage increases, that magnetic field around that conductor increases, and when the voltage decreases, the magnetic field around that conductor decreases, and that movement is what actually makes a transformer do work. And so this expanding and contracting magnetic field produces or induces a varying current in the second coil, and we're going to see that with some animations here in just a moment. The power is transferred between the two coils through that electromagnetic induction. So here's a good representation here of the expanding and collapsing magnetic field. This would be the first coil, which we're going to call the primary coil. We'll get into terms in just a minute. But as you can see, that expanding magnetic field is actually cutting across this second coil, which is what we call the secondary coil. And this is, the pulses here are very slow. They would happen extremely fast, but this animation here is showing you, if you had a lamp on that side, that when you are cutting these lines of coils in this secondary transformer, you're actually producing some current, and then if you have current, you have a voltage drop across the lamp, and the lamp is energized. It's energized while the magnetic field is either expanding or collapsing, but as we know with AC, the AC sine wave, it is sometimes it's passing through zero. And so there will actually be a time that the lamp is off. Now, we don't ever actually see this because it's happening so fast, but if you were to take a movie camera that the frames per second were extremely fast, faster than 3,600 times a second, you would actually see the lights in your house actually flash on and off like this. But it happens so fast that it isn't visible to the naked eye. This is a pretty good animation that shows what's actually going on inside a transformer. Again, we have the first winding, which is where our power source will be connected to. And we have a second winding here, which is where our load will be connected to. And this shows a sine wave coming in, and we're going to talk about this in a moment, but transformers only work on AC, alternating current, because alternating current changes, DC does not change, and we need that change for this electromagnetic induction to happen. That smells like a test question to me. Whether transformers work on AC or DC or both. But here we have this sine wave, which is causing current to flow in the wire. When the current flows, we're causing this electromagnetic induction to rotate around that wire. And we learned from the electromagnet that we studied that those magnetic lines penetrate this permeable soft iron core, and soft iron can manipulate those magnetic field lines and get them to go in the direction that we want. And so you see them, they're rotating around here in a counterclockwise fashion, and then when we get to the negative alteration, they're rotating around in the opposite rotation. That magnetic field then, in turn, is expanding and collapsing on this secondary winding, and when it expands and collapses, it produces a current, and that current can then be plotted, current and or voltage. Once we have a load here, we would have a voltage drop across that load. This transformer has the same number of turns in the primary as the secondary, so the amplitude of our sine wave coming in is the same as the amplitude of our sine wave coming out. But we can actually play around with the ratio between these two windings and be able to change the amplitude of one versus the other. We're going to see that in here in just a moment. Let's talk about the types of transformers. There is single winding transformers. These are less popular, but they are out there and they do exist. If you think about the voltage divider that we studied in just a few sections back, a single winding transformer called an auto transformer is much like a voltage divider. And then there is also a single winding transformer called a variable auto transformer. In the field we pretty much call them variacs, but it is an adjustable single winding transformer. And then we have two winding transformers. That's what we were looking at on the animation in the previous slide. And as I said, we could step down the voltage by varying the amount of turns that you have between the first winding and the second winding. And in the field we have a term for that. We call it a buck transformer. We're going to buck it down, the voltage. We could step up the voltage. So our first winding could have, let's say, 120 volts, and our second winding we want to output 240 volts. That would be a boost transformer. That's kind of a nickname we have for it out in the field. And then there's an isolation transformer. That's exactly what we were looking at on the previous page. Isolation transformer has the same number of windings on the primary side as we do on the secondary side, and we use that for the express purposes of isolating, specifically grounds, and we use those a lot in control systems. When we bring power into a control system, we don't bring a lot of the noise that we can find in building steel in the plant, so we will isolate it through an isolation transformer before it actually comes into the control system. Let's look at some terms for a transformer. Winding. A winding is an inductor or a coil of wire within the transformer. So we, in that animation, saw two windings, and they're going to have some specific terms. And then those windings are typically around a core, and that core is made of some permeable metal base that we can use to manipulate those magnetic field lines to go in the direction that we want them to go. Okay, so the term winding, we have separate windings, so we want to be able to discern one winding from another. A primary winding is the source side. That's where we're going to tie in our power source to of the transformer. Okay, I have a little asterisk here because this is not for an auto transformer or variac. It is for a two-winding transformer. And then the secondary winding is going to be the load side. Okay, it's going to be what gets acted upon. The primary winding is the actor. It's producing the magnetic field, and the secondary winding will be the consumer. It will tie to the load, but it will be the one that's consuming that magnetic field, and it's either going to be a step up, step down, or isolation transformer. Okay, and again, I have a little asterisk here. You only have two windings in a two-winding transformer. In a single winding transformer like a auto transformer or a variac, we'd only have one winding. The turns ratio is just the number of turns of the primary versus the number of turns in the secondary. So we don't actually, if a transformer has 16,000 windings in the primary and 8,000 windings in the secondary, we don't actually list that on the drawing. We're going to say that that's 2 to 1 because there's twice as many turns in the primary as the secondary, but we'll look at that in just a moment. So here is a schematic of an autotransformer. This is our symbol for a winding, and it kind of is there to depict a coil of wire. And what these are actually taps. So we have just one winding in our variac, or our autotransformer. And then we have these taps here. And these taps are at different places along the windings, and we're going to get different voltages out, much like we do with a voltage divider. So the tap up here would just be our total voltage that we put in. So if this is 120 volts coming in, off of this tap we would have 120 volts. Out of this tap we would have maybe 50 volts. It looks like it's a little less than half. So that would be a 50 volt tap. Down here we would have maybe a 25 volt tap and then maybe a 10 volt tap. Okay, so it's just a way to be able to divide up an AC signal without having to build a voltage divider. We can just use an autotransformer to get varying voltages off of a source here, a single source. Okay, a 2-winding transformer, this is the one that's much more common, and this is my schematic for that. So we have the primary side, and 99.9% of the time we're going to depict the primary side is going to be on the left side, and the secondary side will be on the right side. We'll see that in a minute. So this is just telling us that this entire side here is the primary side. The actual part of the transformer is literally just this little area here. The rest of it is the wiring and connecting it to either the source or the load. But this primary side has the primary winding of the transformer. And then the secondary side, we have the secondary winding. And if you notice, there's actually no physical wires connecting between there. And when you get into the lab, we're going to experiment with that a little bit more. But the connection between there is electromagnetic. It's not electrical. It's electromagnetic. So that's one of the reasons why a transformer is good for isolating things, is there's physically no electrical connection between the two. And then here's that turns ratio that I spoke of. Now, there's not physically 2 turns on this side and 1 turn on this side. What this ratio is telling us is there's twice as many turns on this side as there is on this side. And the actual number of turns that's inside the transformer is immaterial to us. All we really care about is the ratio for us to be able to calculate quantities. In between the 2 coils, I show these 2 parallel lines. Those 2 parallel lines mean that we have a soft iron core. Now, it is possible to have a transformer that does not have those 2 lines depicted, and that would be an air core. That would be more in like radio and transmitting type circuits get into air core coils and transformers and things like that. But in the power field, we will always want to be able to harvest as much of that electromagnetic produced field as we can, and we do that through that soft iron core. Okay, so here I want to continue to look at our transformer. This would be our primary voltage. Now, a couple times in the electrical field, we kind of switch nomenclatures on you. So what did I always have here before? I had E sub S for the source voltage. Well, we've moved E sub S over here, and I'll explain why in just a minute. So I have supplanted the E sub S that we've seen in so many other depictions of circuits with E sub P. That just means that it's the primary side of the transformer. And the N is the number of turns, and again, it's not physically the physical number of turns. It's reduced down to a ratio that is something that's easier for us to understand. But the N sub P means that's going to be the turns ratio for the primary side, and then we're going to have a primary current, and I would use I sub P to depict the primary current. And then we have the same quantities on the other side. Here again, E sub S has now been moved over to the load side. So when we're talking about transformers, at least, E sub S, we're going to be talking about secondary load voltage. So please don't get that confused with source voltage when we do transformers. Okay, and then the secondary turns ratio will be N sub S, and the secondary current will be I sub S. Okay. So here, let's look at just the turns ratio. And here, I'm actually physically showing the number of turns that we would have. Now, visually looking at that, it's quite hard to understand what that is quantifying. But if we just take the turns ratio from the primary and we divide it by the turns ratio from the secondary, that's going to be a 2-to-1 transformer. Okay, so that's just helping us to understand why we don't show the physical turns on a transformer, that we really just want to see the ratio, because it's easier for us to quantify looking at a simplified fraction like that. Okay, let's look at the relationship between current and voltage. So in this particular transformer, I have a 2-to-1 ratio. I had twice as many windings in my primary as I do in my secondary. So because I have twice as many here, I'm going to be producing more magnetic strength than I'm going to be consuming. I'm only going to be consuming half the magnetic strength that I produce out of these windings. So that's why my voltage is going to go from 240 volts down to 120 volts. So we're going to call this a buck transformer, or a step-down transformer. And so my voltage steps down, but look at the quantities of my current. My current is actually being stepped up at the same time. So even though on this side I am outputting 1 amp, on this side for that load I will be consuming 2 amps. So actually the apparent power that I am consuming on this side is going to equal the apparent power on this side, and we're going to see that in a moment. But except for some efficiency losses, we're going to, across the transformer, we're going to have the same amount of power on either side of the transformer. But it's very important, the concept of, if we're stepping down the voltage, we will be stepping up the current, and that's going to keep our power differential basically the same. Okay, so just a thought experiment: if I step up the voltage, what's going to happen to the current? It's going to actually be stepping down. Okay, and obviously if it's an isolation transformer, the voltage stays the same across the transformer, the current's going to stay the same across the transformer. Okay, let's look at some of these formulas for being able to quantify some of these values. So transformers are rated in volt amperes. Okay, it's not watts, it's volt amperes. And when we get into the power triangle, we're going to understand why we call it volt amperes and not watts. But just for now, take my word for it that they're rated in volt amperes. And if we get above 999 volt amperes, we say they're kilovolt amperes, or out in the field, a lot of times we just say kVA. Okay, and this is a very important. This smells like a test question. The transformer's rating, which is typically stamped on the transformer, is based on the load side. Okay. Now with losses, we're going to have just a little bit higher rating on the primary side, and we'll get into transformer losses in a future slide here. But on the load side, if I have a 500 volt ampere transformer, that's 500 volt amperes that I can put on the load side. Okay, that's probably going to be a test question. A 1 kVA transformer whose secondary voltage has 120 volts could handle how many amps? Well, if we have 1,000 volt amperes or 1 kVA, all we have to do is take that 1,000 volt amperes and divide it by whatever voltage is at that rating. In this case, 120 volts. That's going to be 8.3 amps. Okay, and because all transformers are rated on the secondary side, I would be able to put 8.3 amps of load on that. If the transformer ratio is 2 to 1, what would be the primary current? And I'm speaking of this same transformer here. Remember, if we're stepping down the voltage, we're stepping up the current. So that means my secondary current would actually be higher than my primary current. So I don't multiply this by 2, I actually divide it by 2 to get to my primary current. So there is 4.3 amps, I'm sorry, 4.2 amps for my primary current in a 2 to 1 ratio. Okay, and that's for an ideal transformer, one that has no losses. We'll look at what we need to do for losses in here in just a minute. And here it is. Transformer efficiency. No transformer is 100% efficient. There's always going to be some losses. Okay, most are 90 to 99% efficient, but I have purchased transformers that were poorly constructed that have been down in the 70%. And you're going to be calculating some of those quantities in your lab this week. So you'll see some transformers that are up very high, and you'll see some that are quite low. And it's just based on the construction materials and those sorts of things. Efficiency is pretty easily calculated. The power that we get out on the secondary side, we divide it by the power that we put in on the primary side, and that gives us our percent ratio. Excuse me. That would actually give you a decimal, so you'd have to multiply by 100 to get the percentage. But that's our simple formula: power out divided by power in. Transformer losses happen in 2 categories. There's going to be losses that happen in the copper. And copper is basically just our windings, right? Our primary winding and our secondary winding. If it's an auto transformer or variac, it's just going to be one winding. And then our core losses, and that's the non-copper losses. And those are losses that are either electromagnetic or within the soft permeable core. Okay. So let's look at these losses in detail. Copper losses. Copper losses happen in the windings of the coils. Okay, that's the only place that there actually is copper in a transformer. And the first one is termed I2R loss. It's kind of an odd terminology, I2R, because the actual formula is I squared R, but for some reason in the field they're called I2R losses. And I think it's much like H2O, but in this case the 2 refers, for water, H2O refers to how many hydrogen atoms there are in there, where this 2 refers to squared. So anyway, in the field, if somebody talks about I2R losses, they really mean just the formula for power, which is I squared times R. And those are primarily going to be in the form of heat. A transformer gets hot, that is watts that we're losing, and those are those I squared R losses. Okay, primary losses occur under power. Okay, so as soon as you hook a transformer to power, you're going to have losses. Okay, you may not actually be transferring anything to the load. If there's an open switch on the secondary side, you're going to not have any secondary losses because there's no current flow. But you will have primary losses as soon as you plug it in. That is why it's a good practice of all of these wall warts that you use to power or recharge your phone and your iPad or your computer. All of those, as soon as you plug them in, start consuming power. Even if you haven't plugged them into your phone or your iPad or your computer. The primary side, there are some losses, and you can see that if you, some of these packs for computers are quite large, and if you just plug it in but you don't have it plugged into your computer, and after a while you go over and you touch it, it's warm, and those are the I2R losses on the primary side of the transformer. So you're actually spinning a watt meter and running up an electric bill, but you're not actually using any of that power. Secondary losses happen only when it's under load. By definition, you have to have current flowing through resistance to experience these I2R losses, or the power and heat losses. And if we don't have a load on the secondary, we're not going to experience those losses. So primary losses will happen under power. Secondary losses will happen under load. Those sound like test questions to me as well. Transformer core losses. Core losses are in the core of the transformer. That's a very definitive statement. That makes sense, right? Core losses are in the core of the transformer. They come in three varieties. The first one is eddy currents. The best way that I can describe this, if you've ever been on a float trip or ever just been around a river and there's a boulder in the middle of the river, and as the water flows by the boulder, you'll see kind of a swirling pool behind the boulder. Those are eddy currents. Those are actually in water. Well, when we have currents flowing through our permeable soft iron core, we get those currents as well. I have a graphic that's going to show those. Hysteresis. Hysteresis is basically the resistance to change of magnetic field inside that core. So I had that animation where we were rotating around in a circle, that soft iron core, and but then it would alternate as soon as my AC signal changed to the negative alteration. And whenever you seesaw something back and forth like that, there's always going to be resistance to that change, and that's what we call hysteresis losses. And then we have flux leakage, and that's basically our magnetic field lines just do not penetrate the secondary coil, and that's wasted energy. We're going to look at each one of these in depth. So the magnetic flux created by the primary coil induces a current in the core. Okay, so here is our soft iron core, this gray box here. This is my primary coil, and these are my magnetic field lines, the flux that is penetrating that soft iron core. As soon as it does, it makes these little swirls like we see on a river, or even the swirls that happen behind a semi-truck going down highway. If you've ever seen rain as it comes over the top of the truck, and then when it hits the back of the truck, it'll kind of make a swirl around the back of the truck. Those are eddy currents, wind currents that are produced by the truck. That same phenomenon happens inside the core. Here's a little bit better depiction here of what happens. If we just had a solid block core, we'd have these big eddy currents. And so when you look at the transformers in lab, you'll notice that the soft iron core is actually a whole bunch of steel plates stuck together. And so they're laminated as well, so there's physically no electrical connection between one lamination to another, and that is a physical barrier to keep these eddy currents extremely small, and that keeps that eddy current loss extremely small as well. But they're still able to manipulate those magnetic field lines and get them all to rotate in the pattern that we want. But we actually use laminated plates just to keep those eddy currents from losing too much of the magnetic fields. We want those magnetic field lines to basically be linear. We want it to be moving in a single direction. We don't want these little swirls, because that is not cutting that secondary core like we want it to. Okay. Hysteresis. This is a little animation that I created for hysteresis. We have, remember, we use these blue arrows to depict a domain. And again, a review of the definition of a domain is just a collection of atoms that all of their poles are lined up and pointing north to south together? Well, if we take those collection of atoms, the domain of atoms, and continually keep messing with it back and forth and back and forth, there's going to be just a certain amount of resistance that the core is going to have to wanting to change. It's like everything else. If you have the tide of the ocean, there's a resistance. The beach is resisting that change in the tide of the ocean, and that's the friction between the ocean and the beach causes resistance against that change to happen. This change in alternating current is causing this change in magnetic field, which changes the domain orientation north to south, and that soft iron core has a resistance to that change, and that's what we term hysteresis. And then the last one is flux leakage. So this animation, I think, shows it well. There's magnetic field lines way out here that are not even coming close to penetrating this guy. Now, we design a transformer much more efficient than this. We don't have a coil here just next to a coil. They're right on top of each other, and we try to minimize this flux leakage. This is just an exaggeration so you can kind of understand the concept that not all those produced magnetic field lines are consumed by the secondary coil and therefore will not be used, and that is terms of a loss. I kind of show it here as well. If we have a circular iron core and our primary produces magnetic field lines, these right here will never actually penetrate this secondary core here because they're not going through the soft iron core. They're not being routed to point them in the direction of the secondary coil, and they are never going to produce any current in that coil. So that is a term of a loss. Okay, so efficiency. These losses, all of them, make it physically impossible for a coil to be 100% efficient. So every transformer has those losses in it. Okay, I want to make that clear. So every transformer would have those particular losses in it. And again, power out is going to be the power in minus our losses. So we're going to have a certain amount of power losses due to those three, the eddy current, hysteresis, and flux leakage losses. And we're going to have to subtract those from the power that we put in here. So we're going to have a reduced power out. And then efficiency is a percentage, and this is the calculation that we looked at earlier. The power out divided by the power in. And of course, power out, since we're always going to have losses, this numerator is always going to be less than our denominator, so we're going to be less than 100% efficient. This means that a 1 kVA transformer has to be overbuilt on the primary side. So remember, all transformers are rated on the secondary side. So a 1 kVA transformer means 1,000 volt amperes can be output by the secondary winding. Because we have these losses, our primary winding is going to have to be able to handle something more than 1,000 volt amperes. It might be 1.01 volt kVA, but it will have to be built to handle the losses that are going to happen within itself. So if we say that our transformer is 96% efficient and our kVA is 1 kVA on our secondary side, our primary side, all I did was take this 1 kVA and divide it by 0.96. We actually get what the primary has to be built for. So in this case, if I have 1,000 volt amperes divided by the 0.96, that's what the primary side would have to its apparent power would be for a 1 kVA transformer if it was 96% efficient. Okay, so let's review. What is the definition of a transformer? And it would be good just to stop the video and have the students answer that. My dog is trying to answer it here, but so go ahead and pause the video, and I want you guys to just give your definition of what a transformer is. Okay. List the different types of transformers. Again, let's pause it, but think about previous slides, the different types of transformers that we talked about. Okay. List specific terms as they are associated with transformers. Okay. Let's try to list as many terms for transformers as we can, and all the parts and components that I talked about. So go ahead and pause the video. We'll answer those. Okay. Identify the different types of transformer losses. There's two major categories, and then within those categories there are some subcategories. So try to list the two major ones, and then list the minor ones under each one of those. Okay, so go ahead and pause the video. Okay, let's work this problem on the board. So if I had a primary voltage of 66 volts, I had a primary turns ratio of 3, a secondary turns ratio of 2. Now in some of the earlier ones I showed you that the secondary ratio was always 1. So it was like 3 over 1 or 2 over 1. It doesn't have to be that way. It could be 3 to 2. So this is 3 halves is our ratio. And then our load on the secondary side is 440 ohms. So let's work through this problem, and I want you to figure out what the secondary voltage is, what the secondary current would be, what the volt amperes then of the transformer would be, and then I want you to find the primary current, and we'll assume 100% efficient, and find the primary volt amperes as well. Okay, and that will conclude the review of this transformer lesson. Thanks.